So let's look at some more details in current, mainly current distributions and magnetic fields from such distributions. So there are two main types of current distributions. There's a surface current, which we usually call vector K, and a bulk density, which we usually call either little j or capital J. We'll look at both of these distributions and relate these to the current I. So remember that currents are moving charges, and if they're passing through B fields, they'll experience forces via the Lorentz force, which is V sub I operating on the ith charge V cross B, where V is the velocity of that charge. Q sub I is just one of the moving charges, and normally we would add up the effects of many charges to get a total force. And just to remind you, later on we're going to show that current represent moving charges generate magnetic fields. So just to review of what we said before about current density, this is the volume current density. If you have a uniform current distribution, then let's say it's going down a conductor or a wire that has a cross section A, and there's no difference in current over this cross section, then we can define J as simply the current divided by A, where the direction of the current density is in the direction of the current flow. So if n hat is the normal to the cross section that we show here, which is basically perpendicular to the walls of the wire, the vector J is I over A times this unit vector. The magnitude of the current I, if it's uniformly distributed, we derived last time, is equal to the charge density times the charge of one element times the velocity times the area. And remember, n sub q is the number of q's per unit volume, so that's the number density of charge, and v is the velocity of q, and before we took this as the drift velocity. So these are interchangeable for what we're going to discuss today. And of course A is the cross-sectional area of the conductor. Let's not forget though that the volume charge density, which we call rho, is equal to the number density times q. So if you wanted to, you can write I in terms of rho, as we've done here. So the magnitude of the volume current density, we just take any of these expressions and divide by A. So for example, if we take this current up here, divide by A, we end up with J equaling NQ, Q over V. And now if we use the volume charge density, we can replace that here, and so we'll have J is equal to the volume charge density times the volume. I think if you think about each of these equations, it's pretty obvious that they make sense. Another property of J is that sometimes it's not flowing in the direction of some surface that you're interested in, and so they're basically a difference in direction, so that you could have this angle, say, between J and the surface normal. What we want to do in terms of the component of J parallel to D sub A would be actually related to the current flowing through D sub A. So the current passing through this surface element, you could call dI, because this is a differential in A, would be equal to J dot dA. So dI is equal to J dot dA, and I put a prime on here just because we may be integrating over a dummy variable. The direction of dA is normally chosen to facilitate the flow of J, so whenever possible you want to make dI positive. It's not necessary, but it is convenient. So what that means is that if J is generally heading in this direction, choose dA this way instead of this way. Okay, so let's generalize J a little bit. Before we had uniform J across the cross section. But let's consider a conductor that has a current I entering and leaving it. So I've shown these here with these vectors. Remember, I can sometimes be treated as a vector. And we let dA be a small volume inside of the conductor. And this is part of a surface, S prime, which goes all the way across and fills the cross section of the conductor. This surface right here would be 1, so would this one, but now we've got sort of a general one, S prime. And the thing to remember is that all of the current is being intercepted by this surface element. As before, we take a little element of surface on S prime, and we'll call it dA n hat, where n hat is perpendicular to the surface. And we have now this current density, which is not a constant across the cross-section. So it's defined in terms of a position vector r prime. Here we've got dA, a small surface element on S prime. dI is the current through dA, and you can consider this small enough that the current is uniform over that. So basically what we're saying is that we have a dI that's going through this little element, and what I've said before is that we use the normal vector to give us the direction of dA. If we look at what we had for a uniform system, J is constant over this area, this small area, is just equal to J dotted into the dA, which has the direction n hat. This is the portion of I passing through dA. Most often we are able to choose S prime so that those are parallel, but it doesn't have to be parallel with the unit vector n. Just to remind you, all of I passes through S prime. So another way of saying it is S prime catches all of the current. But in general, this quantity here could vary throughout the conductor. If we integrate dI over S prime, we would expect to get the total current. I will be equal to the integral over, let's make this S prime here, J dot n hat ds. And we've seen equations like this before for electric field. This is like a flux, so I is the flux of the current density J. Now let's look at the magnetic force on a volume current element. Let's suppose we have a B field that penetrates the conductor, and we take a small d tau prime, which is our friend dA, times a vector dl along the direction of current flow. So if Q is positive, we then have for the Lorentz force this equation here. And that is equal to a element of the force, and that would be on a single charge Q. Now I want to make sure you understand what we're going to do, where we're headed. We're going to keep getting dFs for larger and larger collections of charge. And so what we're changing will be the volume that contains that charge. So one more time, this is just a single charge, the force on that. So now we take a volume, and this is a small volume, so we can consider that the current through this surface is constant, and we can consider J constant throughout this volume, so it's small enough. So if you take that d tau prime, so this volume is d tau prime, shown here, the volume element is equal to dA times dl, and the vector dl is in the direction of J, which is in the direction of V. So all of these are headed in the same direction. It's going to be handy to use this identity here. Because V and dl are in the same direction, we can either use the vector part of V or the vector part of dl, and we'll get the same answer. So what I've done here is the scalar dl, the length of the vector dl, times the vector V is equal to the scalar V, the size or the magnitude of V, times the vector dl. So what's the charge contained in this volume element? Well, it's equal to the charge density, the volume charge density, times the volume. And that's the volume of this little element here. So the force on that volume element, which we call d tau prime, the force on that is equal to, again, the Lorentz force. This is the total charge in that volume element, and this is its velocity, and we cross that into B. So that's like the single charge equation, except now Q is replaced by the charge within the volume. So this is the force on the charge within the volume element. Well, rearranging that, we're going to bring dA over here. We'll flop these back and forth. We'll have rho sub Q V times this cross product times dA. And that could be ds, by the way. Okay, now we're going to take the volume element and keep dA on the surface, S prime. Here's our B. Here's our entire conductor. S prime is a surface which basically subtends all of the cross-section of the conductor. Here's our dV, our d tau prime. And we're going to take that and move it around S prime so that we cover all of S prime with our dAs. So all the dAs associated with the d tau primes are in the surface S prime, and this intersects all of the current. So if we add up the forces on each of these volume elements, we get the magnetic force acting on a differential of volume that looks like this, because we've got a dl, we've got a surface S prime, and we displacement along dl, and we make dl small enough that this surface back here also subtends the conductor. So we have a charge contained in here. It's moving with velocity v in the direction of dl, the vector dl, and it's interacting with the B field. If we take then the df acting on little volume element, okay, remember that's this little guy here. It doesn't look so little, but it is. This is what that value was. And if we integrate that over the surface S prime, we will get the differential of force on this volume. This is dv prime. See, this is dv prime right here. So we integrate over S the differential of force on the volume d tau, and we get this expression right here. So all we've done is take this df and put it right here. And I've switched dA to ds prime. If we look at this in the volume, dl is a constant and b is a constant because this is so small. The b does not change over this region here, and so dl is always a little constant, so we can bring it outside. So what that means then is that we have this surface integral of this quantity right here. If you go back, this quantity right here is the current. It's a differential of current. It's the current passing through our small volume element right here. So the current passing through dA we'll call di, and so now we're integrating over the surface S prime all of the di's. Well, remember that di was defined like this. We switched it to a volume charge density times the velocity, and we know that if we integrate di over S prime we get I. So we come down now to the differential of force on this volume element is equal to I times dl cross b. Well, this is a pretty useful equation because we're starting to get now larger volume elements that we can then find the force. If we now repeat that here and consider that the conductor is making a complete loop where dl is the differential of length in the direction of the current flow anywhere along the loop. So if current is flowing this way, then anywhere you want you can put a dl in the direction of current flow, and that represents the current flow over the entire cross section of the wire. And so up here it would be heading in this direction. Here's our old B field. If you call this loop C, so this is the path that we're going to be considering, goes around the entire loop, the curve C. If we take this loop large enough so that it's large compared to the cross section, let's say just a distance here across the conductor, then C is a line. So then we can find the force on the entire loop by doing a line integral of df on the element dv prime. Remember, dv prime is a little volume element that might look like this, times dl. Okay, so to find the total force on the loop, we do the line integral along this path C of the differential of the force on that volume element dv prime. So this is a dv prime right here, and there's dv primes everywhere along that loop. Here's our differential, the same equation above. Find the force on the entire loop. We do the line integral of dl cross b times the current I. Remember, I is the same at any point along C because it's the total current going along the loop. Okay, so this is an interesting and important equation because it allows us to find forces on current loops. So here it is again, the force on the entire loop, and so we realize that the differential in this loop is dl. So when you take the cross product you get a vector, but for example in Cartesian coordinates you'll have components where this is dx, dy, dz. Well, we can write this in a different form. This is an important equation, but another form is to go back to volume elements. And so if you take this df on the differential length dl that we had previously, we can write that in terms of j, and that's done as follows. You take I dl and turn it into j by multiplying j times dA, and then here's our magnitude dl. So df on dl is equal to j cross b times dA dl. And realize that that is a volume element. So that means that the differential of force on that particular element is equal to j cross b times d tau. And if you wanted to, you could put primes on that. So now, what are we going to integrate? We're going to integrate over the volume of the entire loop. So here you would have j cross b d tau prime, and we can put a v prime if you wish. The volume of the entire loop, that would be equal to the same force on the entire loop. So all we've done is use the fact that I and j are related, and there's a volume element involved that we can use to get us a volume integral. To remind you then, both equations are useful. This latter equation is more general in the sense that the current need not be confined inside of a conducting wire. And so therefore, systems like plasmas quite frequently use this equation. In terms of other factors, remember that J does not have to be uniform throughout the volume. And so you can even have regions where it is zero. To get anything interesting, you would have volumes where it is non-zero. The other thing is that B does not have to be uniform. In fact, if it's uniform, I'll show you that things get kind of uninteresting. So at points along the current path, you could have B, which is zero, for example. And it rarely is in a real situation. You have B's that are penetrating the entire volume, but there are several where you don't do that. Let's take a case of uniform B, and here the net force is on a closed current loop, and this is all immersed in a uniform B. And so if we look at this, the net force will always be zero. And this could include very crazy loops, as long as B is constant over those loops. And so how do we see that? Well, we take the force on the entire loop or wire, and we integrate I dl cross B around the current loop. But if we factor out the I, and we take and combine dl with the integral, because B is a constant, we can do that, then what do we have? We basically have the integral of dl around the current loop. Okay, so here's the current loop, and you take all the dl's and you go around the loop and add up all those dl's, you're going to get zero because you end up at the same place as you left. And for every one here, there's another one somewhere that's going this way that will cancel it. So I think you see then that this is equal to zero, so you conclude then that the force on the entire wire is equal to zero. I just want to remind you though that you can have zero force, but you can also have a net torque. And so it's quite often that you have zero force, but the net torque will not be zero. And this is important for motors and old current meters, the ones with needles, which cause the needle to turn when you put more current through the wire. So let's quickly take some very trivial examples. And so if you have a current I distributed over a wire where the current is uniform, then if it has a cross-section with radius A, just find the volume current density. So if you take the current S surface inside, it doesn't have to be on the ends, that is normal to the walls of the cylinder, then ds is equal to ds magnitude times the unit vector k, as we show here. On S, this will be parallel to the walls of the cylinder, so then J, which is in the direction of the current flow, is just equal to J k hat. And so it's in the same direction as ds prime. Well, okay, di is equal to j dot ds, and so in magnitude is j ds prime. So because it's uniform, j is a constant, And so therefore, if you integrate over the surface, so remember this is S up here, then that's just j pi a squared, because j comes out and you're just integrating over ds. Well, solve for j. And so this is the magnitude of j. It's just the current over the area cross section pi a squared. And this means that j is equal to I over pi a squared. And now we put in the direction, which is k hat. Here's another one where j is not constant. It's equal to k times r. And if we look at the expression for ds, if we notice that j is perpendicular to ds prime. So again, we have the magnitude of j times the magnitude of ds prime is equal to di, because these are in the same direction. So do the same thing. We take I to be the integral of j dot ds, which is the integral of j ds. Put in our r dependence for our j, take our ds to be r, dr, d theta, and then bring the k outside, integrate over d theta, integrate over r, and of course this goes from 0 to a, this goes from 0 to 2 pi. This of course gives us our 2 pi. And so the current then is equal to 2 pi k r cubed over 3. Suppose the current is distributed with a different function. This is 1 over r. And so it's basically the same deal. We therefore are going to take a lot of shortcuts. Here's j. We'll let it be c over r. And if we take the integral over the cross section of the wire, the surface integral, because they're headed in the same direction, j and ds prime if you wish, that's equal to the current. So these are scalars right here. Put in our j scalar, which is c over r. Let's forget about the theta integral. This is just 2 pi r dr. So if we bring the integral here, this is the integral, we would have c times 2 pi r from a to 0. Realize that this r and this r cancel. So we're really integrating a constant, so therefore we get a factor r here. So this is equal to 2 pi a times c. So you can evaluate this for c, put it back into j, and we get j equaling I over 2 pi a r times the direction of j, which is k hat. So these are just some simple examples of finding current or finding the current density that have functional form. Now let's talk about surface currents. If current is flowing over a surface S, it is usually described by a surface current density, letter K. K is the current per unit length, perpendicular to the flow. Now this is a difficult concept. K points in the direction of the current flow at a given point. Okay, so consider a very thin layer of positive charge moving along the direction of K. We're going to have to assume that this is a very small, infinitesimally thin layer. If K is a constant everywhere on this surface, then if we have a total current I flowing along on this surface, the K is defined as the total current divided by the length or width of this surface current. So this line that I've drawn here is perpendicular to K, and if that's the case, then we have capital K being the current divided by length, the width of the place where current is flowing. In this case, the z hat would be a vector parallel to K. Okay, so this is a very peculiar case where K is a constant over the entire width of the surface. Now let's take another version of this. We've got a very thin sheet that's indicated by this surface here, and we have a total current entering that sheet, and I've tried to show it being distributed over this width here. And so if we took a very small width line here, so it has a width of ds perpendicular, and has, for example, to form an element along the direction of current flow, it'd have ds parallel. The ds perpendicular is the differential of width in the strip that's perpendicular to the current flow at that point. ds parallel is a differential along the current path at the same point as d perpendicular. So I drew these separately so we could see them, but normally this would be up here, so something subtending that area there. So by definition, for a local current density, if we take the dI being the current in this little strip here and divide by the perpendicular distance across this strip here, that will be equal to K. And this is really the definition of K for a local K on a surface. So here's our definition again, and so we'd like to look at the function K as a function of the surface charge density. So for that we're going to need to take an area, and so we start with this surface area here, which will be related to the two distances that we've already shown. So if we multiply these two together, we'll get a dA. So that's what we see here. dA is equal to ds perpendicular times ds parallel. Okay, so let's come over here and look at the dI. dI is the current that's entering this little area along this direction here. And we know that that's dq dt, so dq entering into this region is going to be equal to the charge density times the area, which is dA. So let's put in dA in terms of the ds's. So this is dA right here. We've got two differentials, but we can eliminate one by the fact that the rate of change of the charge, the distance ds parallel with respect to time, is equal to the velocity of the charge. Solving for dI then, we can put in our velocity and we end up with this quantity here where ds perpendicular is perpendicular to the flow. Sigma is the charge density on that surface, which could depend on position, and v is the velocity of the charge. Taking di ds perpendicular, which is the definition of K, then we can write that K in magnitude is sigma vq, and since vq is in the direction of current flow and so is K, we can set them equal to the vectors. So that's the vector vk, and this is the vector capital K. And just to remind you, we could have replaced v sub q with the drift velocity. So just remember that at any instant dq into this area is equal to the dq out. So there's no buildup of charge in here. So sigma, in terms of the instantaneous value, is a constant here. We could have K varying over a surface from point to point, and that could be due to variations of sigma with position and or velocity. The other thing that could be possible also is that one or more of these is time dependent, in which case K could be time dependent. Let's go another try for the concept of K, and for that I'd like to consider a line C which crosses over the strip. And just to make this finish, let's go all the way across. Let's let ds be a vector now that's a line element on C that has this small width here, small length, and we're going to define a new vector which is n perpendicular. And by that what I mean is a unit vector that's perpendicular to this little ds and in the surface, so it lies within the surface. Now normally you could decide to go this way or this way, but since current is flowing this way, it makes more sense to put it in this direction here, so that if you, for example, took the dot product with K, you'd get a positive number. Just a reminder, this sheet of current has no thickness. This is saying the same thing, that this vector n hat perpendicular is a unit vector which lies in the surface. So here's the picture again, and we're going to form di in terms of a dot product. Because if you have a vector n perpendicular n hat going in this direction, and you have K in this direction, if you want the component of K which is perpendicular to ds vector, then the dot product will give that to you. So that determines the component of K normal to ds. Okay, so when we integrate, this is di. So when we integrate di over the length of the line C, which is generated by all the ds's, we get that the total current is equal to I, integrated over C the quantity k dot n perpendicular ds. To reiterate, in terms of a surface charge density, kappa is equal to sigma times v. If n sub q is the areal number density of charge, then we can represent the charge density in terms of a charge per unit area times q, the number of charges per unit area times the charge per particle. So we can write k in terms of those quantities right here. The units of k are amps per meter, because realize again that it's the length of that little element rather than any kind of area. So it's a current per unit length, which is the width of the element. As we did before on the volume charge density, let's look at the magnetic force on a surface current. We consider this surface current the vector k r prime, and that's on a surface s prime. And we want to know the force on s prime, where the position that we're talking about right now is defined by the position vector r prime relative to the origin. And of course we have a B field, which is given by this arrow here. So we need to find a current dI corresponding to a small element at this position here. So we use the same idea, and we have this ds perpendicular and we have this ds parallel. The ds parallel is going in the direction of k, and so that defines an area. If we take the product, we'll get a dA prime. I'm repeating this here. By definition, the current that's entering this small area is equal to k times the distance across this area element in the perpendicular direction. So in other words, the distance that crosses k in a perpendicular manner. But now let's go to the force. So we're going to take dI as our current. So we're simply going to convert our Lorentz force, I dl cross B, to differentials. So in other words, we'll put in a dF here and a dI here. So this will be the differential of F is equal to dI dl cross B. Now dl is in the direction of current flow. So if we take a unit vector in the direction of the surface charge density and multiply by ds parallel, we'll get our dl. So substituting those into here, we have k ds perpendicular times ds parallel k hat, and then this is crossed B. So this is I dl cross B. We put in for k hat, and that gives us then crossed into B times the area element ds hat, and that comes from this product right here. This right here is the area ds. These are lengths, these are distances. Putting that in, then we have the vector k, here's the vector k, cross B times this area element. If you want to, then you can just consider this is an area element, and if we integrate that over the whole surface, we'll get the force on this surface. And so doing that, we get the force on the surface is equal to k cross B ds prime, and if you want to put primes on all these, you're welcome to. So this is the analogous equation to what we derived for the volume current density. Now we're talking about the force on all of this surface here by integrating our dF over the entire surface. So that gives us the magnetic force due to a surface current. Well, let's just look at an example. This would be just very simple again, like our volume current density. Suppose you have a current I flowing down a wire of radius A. We'll assume that I is uniformly distributed over the surface of the wire, and we're defined capital K, the surface current density. So all this current is flowing out on this surface. We're going to consider a line, this line here, which is a circle on the surface in a plane that's normal to the direction of the current flow, which we'll take as the k direction, k hat direction. We could think of our current as being a vector then, so that would be I k hat. All the current is flowing out on the walls of this wire. K will be the current per per unit length crossing this curve here. And so if we consider then that we have this current perpendicular any line element on this curve, then we can just integrate around that curve to get the current, which will be related to the current density. I just want to mention though that if you take any C that goes all the way around, so just pretend that brings it around, that will also qualify for doing this integral. But because of the symmetry of this problem, it's so much easier to use this circle. If we take K then, current per unit length, of the line on the surface, this C, we have the current uniformly distributed over the surface of the wire, which means that K is constant for any point on C. The magnitude of K is given by the total current divided by the circumference of the wire, 2 pi a. Doing that then, you can solve for K by just taking the direction. This is the magnitude. The direction is little k, and so we have then that K is equal to this quantity K hat. So that's a very simple example. There's no spatial dependence on K. We only worry about the direction of it, and we picked a C that is perpendicular to it, so we get this very simple result. Another important concept is the conservation of charge. The basic idea is electric charges can neither be created nor destroyed. This is the conservation of charge. And as far as we know, every place in the universe, this law is true. If we take current, which is the flow of charge, if charge is conserved, there must be a relationship between the net current flow out of a region and the rate of change of the charge contained within the region. So one way to have a buildup of charge within a volume is to imagine a volume tau with an intense radioactive source that is emitting electrons. Let's imagine that if some of these or all of these electrons were to leave this volume, then the rate of charge buildup within is greater than 0. Simultaneously, there could be normal currents flowing in and out of tau. So let's imagine this tau, this is a volume, and we have sources of beta particles leaving the region right here, and some of those are escaping. If minus energy is leaving, then the emitters must be positive because they've emitted an electron. So as a result, you have a built-up of positive charge because of this emission that has left the volume tau. Considering this again, let's imagine we have a closed surface, and any place on the surface we could have a ds. What happens to the charge density within this object? If you just consider the net or total charge or current leaving tau through S, the surface, it must equal minus the time rate of change of the total charge enclosed within tau. So one more time. If you consider the current leaving this volume through the surface S, it must equal minus the time rate of change of the total charge enclosed within tau. So the example I gave of the electrons coming out means that the charge density inside must be changing. The current out will be equal to minus the change in the charge that's enclosed per unit time. If the net charge per unit time is decreasing, so dq dt is less than 0, the current leaving tau is positive, and vice versa, and that has to do with this minus sign. So the net current leaving the region is also given by integrating J, which is the current density of the current leaving the sample, integrated over the surface. That would be the total current. Just remember that J could be J in, J out, or both. And so we just say J. Since ds points out, if I is positive, it represents a total charge flowing out, the opposite for minus I. The total charge enclosed within the volume tau, where rho is a function of position and time, at a time t is given by the following. So Q enclosed as a function of time will just be the volume integral of the charge density integrating over the position r prime, actually d tau prime, and an nt. So the time dependence comes about because when you do the integral, you get rid of all of the spatial dependence and you end up with a function of time. So coming back to the electron emission, you basically have a charge density that exists inside the volume, and the Q is building up inside. In this case, positive charge is building up. The current is negative because electrons are leaving. If you then integrate the charge that remains via this density of charge, you get the Q that is building up as a function of time. Just summarizing then, we have the current and the charge enclosed, and the current as a function of the current density. Using these equations, we can write down that I is equal to this quantity here, that's this equation here, and then minus d dt of the Q enclosed, which is this equation here. And this is really a restatement of the conservation of charge in an equation that relates the interesting parameter of the system. This leads to what's called the continuity equation. So we have the same equation that we just showed. This is the current density relating to the current leaving the surface through the surface S, and this relates the charge inside in terms of the rate of change. Let's look at this. We had the equation that relates this to the time dependence of the charge density integral. So this is Q enclosed. So then we can rewrite that by just saying that this is equal to j dot ds over the surface S, and the same quantity here. We've replaced Q enclosed with this integral here. This is called the integral form of the continuity equation. This is the net outflow of current. This is the net rate of decrease of the total charge. This is like a dq dt, and this is related to current. Let's use the divergence theorem, and this is the divergence theorem that we're interested in applied to the j dot ds equation. We're going to change that to a volume integral. If we bring the derivative inside the integral, so we take d by dt of this quantity here, this is a function of t only as we've mentioned before, so we can bring the time derivative inside. It becomes a partial because rho is a function of position and time, so we take partial derivatives here. We equate the two sides here, so we equate the divergence term and this term here, and we end up with the volume integral of del dot j equaling minus the volume integral of this quantity here. This holds for any tau prime. So what that means is we can equate the integrands. We equate the divergence of j as equaling minus the change in the charge density with respect to time. And this is called differential form of the continuity equation. One thing to realize, this is happening at a point. This is an equation that is applied to every point you wish. If you take the divergence of j at this point, you will get this quantity here. Let's look at steady currents. This would be where what comes in comes out. So here's your surface. You have this current coming in and the current going out, and those are equal, so we don't have any change in the charge density with respect to time. So that's what this says. If that's true, then it means that the j, divergence of j, is equal to 0. And if you remember, any vector that has 0 divergence is called a solenoidal vector field. If we have steady currents, then j is a solenoidal vector field, and one of the consequences is that if we take any closed surface and do the surface integral of j over s, we can use the divergence theorem to get the following: that if this is 0, then it means that the surface integral of j is equal to 0. This is consistent with no charge buildup. So there's no charge built up or decrease within the surface S. So we come back to the statement charge in is equal to charge out. So I just wanted to make the loop for the case where we have this solenoidal condition. So next time we're going to treat the problem of finding B fields that are due to currents, and we'll start with the Biot-Savart law.